Hello, welcome everybody. I'm Danielle van Dinter. I'm from TNO, which is the Netherlands Organization of Applied Scientific Research. I have a background in metrology and air quality, and I focus mainly on particles, both particulate matter and ultrafine particles. Today I will show you something about particulate matter. For vacuums, our main focus at TNO was the lab testing of the different sensors, which I did together with my colleague Marcus Blom. So let's get into more details. So for today's presentation, I will start showing you something of the lab setup. Then I will show you the different setting. I will tell you something about the different sensors that we tested. Then I will show you how we evaluated the different sensors and the results. And then that will be followed by conclusions and the lessons we learned. And I will give you a quick preview of the fact sheets that we made. So let's start with the lab setup. I also made a movie, so you can also see some more details over there. We built an exposure box, an isolated exposure box. You see a picture over here, also with vacuums sensors inside. This exposure box, we could control both the temperature and the relative humidity. So here you see the different settings that we used, 15 degrees, 25 and 35 degrees. And then the relative humidity settings, 20, 50 and 80%. We had to generate particulate matter. For that we used the device of Pallas, the RBG1000. Which generates particulate matter. Basically how it works, it's like a small cone with dust inside, and there's something pushing the dust up while something else is brushing it away. So that's what we used. As a reference, we used the FIDAS Pallas 200S. The official reference for particulate matter is 24-hour averages, but we were of course also interested about higher time resolutions, so we used this FIDAS as a reference, and we looked at 10-minute time intervals. As you can see, the box is quite full with the different sensors. We had 3 layers with the different sensors, and we were mixing the air as we were going along. Since the box was quite full, we had to test in 2 batches. Both batches were tested at the end of 2018. If a sensor was malfunctioning, which we could see because we were registering all the data, then the only thing we could do was really unplug it and plug it in again and hope that it would work again, because we didn't want to break off the whole experiment. So that's what we did in case of malfunctioning. So that about the lab setup. Here I show you some of the settings that we used, which is for batch 1. As you can see, different temperature and relative humidity settings, which is on the y-axis on the right. You also see the PM2.5 concentration in blue on the left. As you can see, the PM2.5 concentrations are quite high, higher than what you would expect in natural cases in Europe. It was very difficult to control this because the flow is relatively low, so we did our best, but when looking at the result, we do need to take into account that these are a bit higher concentrations that one would expect. Here you see for batch 1 all the settings where we also show the PM1 concentration, 2.5, 4, PM10 and the total PM concentration, which is for the FIDAS up to 70 micrometers. Here you also see the relatively high values. These are averages then over this step setting. You can see PM10 up to 1000. Even 1200 for the last setting, and PM2.5 up 133, and PM1 up to almost 30. Well, it's very similar for batch 2. I won't show you because it's so similar, but yeah, we have to be aware of that when looking at the results. So which sensors did we test? We had in total 8 PM sensors that we were planning to test. You can see the list over here and then separated in batch 1 and batch 2. We decided to test 3 sensors. The other sensors were in Belgium at the VMM to be tested in the field already. So you see we had the Nova Fitness. They were all up to order and working during the experiment. We had the Xinyi PPD42. As you can see, red crosses, there was a malfunction of that sensor, so we didn't manage to collect any data. So I cannot go into further details on that one. Then we had the Xinyi PPD60. As you can see, 2 of the sensors were working, 1 unfortunately not. We had the Honeywell HPMA, which was working properly. Then we had the Dylos 1700. That's the only one who has its own case. And you can see 1 was not working in that case. The Plant Tower, which was in batch 2, which they were all working properly. Then we had the Winson. They were all doing well. And then the AlphaSense, the OPC-N2. This one also malfunctioned, so I won't be able to show you any results, unfortunately. So how did we evaluate the sensors and look at the test results? Well, first of all, we looked at data availability, which is simply the amount of data points in percentages which were available for the whole test period, so for whole batch 1 and for whole batch 2 experiments. We excluded data points where there simply was data lacking, but also where data points were totally 0, because those were clearly malfunctions. After that, we looked at the linearity. So we had a ramping experiments, which I will show you more about in a minute, where we increased the PM concentrations and we had a constant temperature and relative humidity. And for this data, we look at the 10-minute data and we look at the linear regression. So we did a linear fit, we look mainly at the regression statistics, so the R-squared values. Then we have the accuracy, which basically says how accurate the sensor were able to measure the core PM concentration. So this basically states how comparable the PM concentration of the sensor is to that of, in our case, the VIDAS, the reference measurements. If it's 100%, it's totally accurate. If it's less than 100, it means that the sensor underestimates the PM concentrations, and higher than 100%, it is overestimated. Lastly, we checked the sensitivity to temperature and relative humidity. We did that quantitatively, so we had a look at scatter plots, which were color-coded both with temperature and relative humidity, and then we looked if it was sensitive or not. So I first want to show you the data availability, which you can see over here. As I mentioned already, missing data is excluded, of course, and also 0 readings. You can here see that almost all sensors actually did very well. Data availability more than 95% for almost all. Exception is one of the Nova Fitness sensors. That one had a data availability of 46, so almost half. So that didn't perform so well. And then the one of the PPD60 also has a slightly lower data availability with 87%. But overall, we were quite happy with these results. Then I will show you something on the linearity, which we did a ramping experiment, which I already mentioned to you. So during this rampant experience, we changed the PM concentration, so going from low to high over a certain time with the same temperature and relative humidity settings. And here you can see for batch 1, but a similar figure is there for batch 2, how the concentration increased over time. So you see PM1 and 2.5 in blue on the left hand side, and you can see for PM1 we reached values from 0 up to 15 more or less micrograms per meter, and for PM2.5 we reached up to 80. PM10 is definitely the highest. It's almost up to 100 micrograms per meter. And this basically means that, well, this means that between 2.5 and 10 micrometers we had a lot of particles, which is not necessarily you see in natural environments. So that's something to keep in mind. So this data we used. All the data of the sensors we use as is or as stated by the manufacturer, we should use it. And for the Shinyai PPD60, the manufacturer states that you need to calibrate the sensor yourself. That's why we use the data of this ramping experiments to calibrate the sensor. We used a quadratic equation, which you see over here. So y is a times x squared plus b times x. This was also the one stated by the manufacturer that you should use. You can see here the results for the two sensors, and you see that the quadratic equation works very well. However, you also see that above a certain threshold, you don't really see any differentiation anymore from the sensor. So for sensor 1, this meant that we couldn't distinguish the PM2.5 concentration above 77.6 microgram per cubic meter. And for the second sensor, this was a bit higher, so it was above 86.7 micrograms per cubic meter. Yeah, for those data points, we would need to fill in missing data, unfortunately. Let's have a look at an example, how we looked at the linearity. Well, that is simply by a scatter plots, and then we would fit a line. So here you see an example of the Nova Fitness. Two of their three sensors we tested there. Here you see PM2.5 on the left-hand side with the reference on the x-axis and the sensor on the y-axis, and then in different colors the three sensors. You can clearly see that there's a linear fit between the data, and then the R squared shows us how well the linearity is between the sensor and the reference. And you can see the same on the right hand side for PM10. I won't go into details for every separate sensors, but here you can see the overall result. Let's first focus on the R squared, because that mainly states something about the linearity, and then on PM2.5. You can see here in the colors, more or less, I indicated which ones are good, which ones are average, and which ones are less good. So if you see for PM2.5, you see very high R squared values in general. So we see a lot of green boxes, which is very good. So those all have R squared values above 0.9. You can see that there are three which are not green, and that is all for the Winston sensors. So one Winston sensor is still relatively high here in orange, it's 0.87, and the other two have a somewhat lower R squared of 0.63. Now, if we look at the same R squared, but then for PM10, for the ones that measure PM10, we see that also there the R squared is in general fairly high, but we see for some sensors it's lower. So here the plant tower has a less good linearity with the reference of about 0.77, 0.8, and the Winston again has a bit of a lower R squared of around 0.5 for two of them, and one is again a bit higher, the Winston 4, the same sensor that was higher for PM2.5, it's 0.76. Now if we look at the slope, ideally you would want the slope to be close to 1, because that means that they measure around the same value. If the intercept is also 0, I just look at the slope for now, but for PM2.5 you can also already see that it's not close to 1 in general. Best fit is achieved by the Dylos, where it's 0.09 and 0.10, but the other ones are always fairly high, all below 0.4, except for one Honeywell, which is 0.45. If you look at PM10, and as you remember, I told you that we had quite some coarse particles during these experiments, we see that the slope drops quite dramatically, actually. Only the dilos still has a somewhat reasonable slope of 0.4, but the rest are all well below 0.1. So that means they clearly underestimate the PM10 values, which states that they have problems apparently capturing this coarser dust that we generated. We can also see that from the accuracy. As I mentioned, a 100% accuracy is the best, is what you would want. It means it's the same as the reference, and everything below that means it's underestimated. So here you see the accuracies in the table. You can see that the dilos still seems to do reasonably well. It's around 90%. But the others, there's clearly an underestimation of the PM2.5 concentration, and even the ones of the PPD60, the Shinyai, has an underestimation, which is interesting because we calibrated that one this is for the complete batch that this was in, but we calibrated it with this dust that we generated, so that's interesting to see. When we look at PM10, also as it was already indicated by the slope, there's a clear underestimation. The dilos again has the best values for 43 and 46, but the rest is basically all below 10, except for one Nova Fitness, which is doing a bit better than the rest, but still quite low accuracies. In principle, this is not necessarily an issue. If you, for example, are a research institute, then you can just calibrate the sensor, and as long as the linearity is good, this will work. But of course, if you're citizens, you want to take it out of the box and just measure as is, this can be an issue. There's only one sensor which measures PM1, which is the plant tower, and this has a reasonable accuracy, I would say around 70% accurate. So that is it for the accuracy. Then the last thing we looked at, as I mentioned, is the sensitivity to temperature and humidity. It's quite hard to capture this in a number, so we decided to look at scatter plots, as I show you over here, and this is the plant tower that we show here for PM1 concentrations. We see on the left hand side, we see tripod of the relative humidity. So the colors indicate the relative humidity used, so you can see around 20, 50, and then the red blocks are around 80%. What you can see here is for the first sensor, for example, it mainly has some issues apparently when the relative humidity is 50%. When we look at temperature, we don't see this behavior for the plant tower. We do see one of the other sensors, the last sensor, sensor 3, which seems to have a problem with mainly mid-range temperature. So this was interesting for us to see. If I would then sum it up, the overall results in the table, which I did over here, as I mentioned, it's hard to quantify this in a number, so I just looked whether I thought it was sensitive or not. And as you can see, some sensors have some sensitivity, but overall not too much. We see only for the Honeywell, it has a clear sensitivity to the relative humidity. I think that was the one that stood out the most. The Nova Fitness also seemed to have some problems, at least one of the sensors with relative humidity. Then we had the dilos, which has some sensitivity to temperature, and the plant tower, also one of the sensors for PM1 at least, seemed to have some sensitivity. Best is of course to test this into the field, but yeah, the nice thing of the lab is that you can you can decide for yourself the temperature and relative humidity settings. but Jordi will show you some of the field results later on. So what are our main conclusions? Well, for data availability, we can say basically that they were all quite good, except for one Nova Fitness and one Shinyai. Then we did have some issues with 2 others, which we weren't able to test because of this, which is unfortunate. The linearity, overall we can say that they're reasonably good, with our square values above 0.9 for most of the sensors. For plant hours, for PM10, it was a bit less good, so it was in between 0.75 and 0.9. And then the Winson showed the least linearity, with our squared values between 0.5 and 0.75. When we looked at accuracy compared to the reference, overall this was reasonably low, especially for PM10. Dilos showed the most promising result, especially for PM2.5. This was in the order of 90%. Others showed a bit less good results for PM2.5, for example, the Honeywell and the Shinyai. The Dilos for PM10 was also a bit less good, as well as the plant tower for PM1. And then we had some where actually the accuracy was quite low, so below 45%. This was the case for the Honeywell for PM10, for the Nova Fitness overall, the plant tower for PM2.5 and 10, and the Winson for PM10. For the sensitivity to temperature and humidity, overall we thought they were not very sensitive. Some showed some. The Honeywell seems most sensitive to humidity. Then we had some which were moderately sensitive, like the plant tower for PM1 for temperature, and the Dilos also. And the Nova Fitness had some sensitivity to relative humidity. So what can we say overall of the lessons learned? Well, first of all, it's very hard to generate a constant PM value in the lab. We really struggled with that. Which is logical, I guess, to be expected. It's not like a gas which you can simply control the flow very easily. We had relatively low flows in our box, and therefore we had also relatively high PM concentrations, which we need to take into account when we look at the results. From the calibration out of the box, given by the manufacturer, we can say that they in general underestimated the PM values. That is, however, with our relatively high PM concentrations that we did the test under. And this underestimations became most apparent for PM10. There we really saw a very strong underestimation. And this also follows the next point, which that the sensors seem to have more problem measuring the Corsair dust between 2.5 and 10 micrometers. We saw that both by PM10 is more underestimated than PM2.5, but also we saw that the linearity was dropping with lower R-squared values. So that was the lessons that we learned. Everything that I showed is quickly summarized in some fact sheets, which you can see an example of over here, and those will be available. And besides that, there is a report which you can look at. So that was it. Any questions? I'll be happy to answer them.